For 17 months, a signal kept arriving from a place no one could see. It slipped into the dish of a massive radio telescope buried in a karst sinkhole in the mountains of southern China, after traveling 2.5 billion years across empty space. The raw intensity of these fast radio bursts is staggering. In about a millisecond, the time it takes you to blink 10 times, they release as much energy as our sun emits over several days. For over 15 years, astronomers had no idea what was producing them. They debated theories about colliding neutron stars, evaporating black holes, and yes, even alien beacons. Then, in April 2020, telescopes caught a massive, identical radio flare originating right here in our own Milky Way. Matching the energy of that local burst confirmed that these signals are the reliable exhaust of a specific hyper-violent cosmic engine. That engine is a magnetar. It is what's left over when a massive star runs out of fuel, collapses, and dies, squeezing its mass into a hyper-dense sphere about 12 miles across. But unlike an ordinary dead star, a magnetar is wrapped in a magnetic field so powerful that flying within 1,000 miles of one, the magnetic pressure alone would dissolve your nervous system the way water dissolves salt. This extreme environment creates a physics problem. The plasma surrounding a magnetar is so dense and highly magnetized that, in theory, it should swallow any radio signal whole before it can escape into space. Knowing the magnetar is the source leaves us with a paradox. To understand how the burst survives, we have to map exactly where on the star this violent flash is actually being generated. To find that location, MIT researcher Kenzie Nimmo looked closely at a property called scintillation. As the radio wave traveled toward Earth, it passed through cosmic gas clouds, which made the signal twinkle. By measuring exactly how that wave twinkled, Nimmo's team could reverse engineer the geometry of the burst, tracing the scattered light back to calculate its physical size. The origin point they found was tiny, at most 10,000 kilometers across. To put that in perspective, an energy burst outshining a galaxy was being squeezed out of a physical space smaller than a single Earth time zone. A shockwave thrown far off the star would be much larger. The math only works if the radio waves are fighting their way out from deep inside the magnetar's suffocating immediate magnetic atmosphere. That settled the location of the origin. But in 2026, the Sky-Eye telescope team focused on a repeating burst and examined a different property, polarization, which tells us how a radio wave twists as it travels. This line graph plots polarization over time. For 17 months, it held completely steady. Then it spiked to 100 times its baseline, drifting down over 2 weeks. This shape only happens when something extremely dense crosses the line of sight. When researchers mapped the shape of the flare, it matched the signature of a coronal mass ejection, the massive plasma clouds our own sun throws off into space. This specific twist in the signal confirms that the magnetar orbits a highly active, sun-like star. This gives us a completely new model for repeating fast radio bursts. We are looking at a violent binary system, where an extreme, crushed stellar core is caught inside the turbulent weather of an ordinary companion star. Every time the sun-like star unleashes a flare, that wave of plasma washes directly over the magnetar, twisting its magnetic fields and altering the geometry of the bursts shooting toward our telescopes. We tend to imagine the extreme corners of the cosmos as isolated kingdoms. We picture deadly objects like neutron stars and black holes quarantined in their own remote graveyards, far away from any quiet, life-giving stars. But this discovery proves those neighborhoods overlap. The universe's most lethal magnetic monsters share the exact same space with stars that look an awful lot like the one warming our oceans. That small bump in the data is the unmistakable physical handshake of two radically different cosmic objects sharing a single weather system, caught together across billions of light years.